copy that. What does that mean? I'm going crazy.
Siddharth, hello. Hello. Hello.
We can hear you, sir.
Yeah. So actually, F62. So I mean, who is this? Hello.
Sir, I'm Vinay. I'm joining from my phone.
Okay,
I
no
will-
problem. Sure.
I will join in from my iPad in 2 minutes. I'm going to my room.
Okay, no problem. Yeah. So as I see that there are 6 of you are here, of course, I can safely assume the rest of the people, many of you are not interested. Many of the students are not interested. That's fine. What can I do? Okay. So,
Sir, actually, we just had a class. We are going to.
oh, you just
our
had a
room.
class. Should I wait for
Uh,
some time? I mean, this is MTech CS or CRS you're talking?
CRS, sir.
CRS, sir.
And even some MTech students attended class, so they'll be coming back to their hostels.
Okay,
So
okay, okay.
just
So
give-
then
just
I can
give
wait
some
for
5
another
minutes.
5-10 minutes.
Some 5 minutes later.
Yeah, sure. I will
11:45.
wait for the 5. No problem.
Thank you, sir.
Yeah, then maybe let's start in 5 minutes. Yeah, can you hear me?
Yes, sir.
Yeah. So I think let's start now. I think people will join slowly. So before I start, is there any doubts, questions about whatever has been done so far, particularly in this NP complete things? I mean, I expect that there will be some confusion about these things because these are not easy concepts to grasp as such. So we have seen things like what P is, we have seen what NP is, we have seen what reduction is, and we have also, so this is also, we have mostly looked at polytime reduction, and also we have looked at what NP complete is. Right, as we do NP, we have also seen what co-NP is. Are these concepts clear to all of you? Okay, so if it is so, then let's try to just go ahead and try to understand what will we do when we face a problem. Okay, this is the most, I mean, an important thing that we will see. So I have told you about NP complete problems. Now I will, in this, for this class, we'll assume that we know 2 NP complete problems, 3 NP complete problems. One of them is ILP, the integer linear program. This is something you can take it granted. Okay, so let's say we know, say we already know. As I told you, there are things which unfortunately I cannot prove in this class. The other one is the SAT, or sometimes called the circuit SAT. So this is the problem of satisfiability. And let me ask someone there. Sohan Das, are you there?
Yes, sir.
Yeah, do you remember what the circuit SAT is?
No, sir. I was not present in the previous class.
Okay, then when I asked you whether you have understood this concept of NPP and all of them, then you did not answer. Okay. Shubinoy Hatai?
Yes, sir.
Yeah, do you remember what SAT is?
Sir, actually it is, sir, in 8 inputs and with OR and AND gate
Right.
and combine them with a NOT gate
Yeah.
and proceeding in this way after the output.
Yeah. So I mean, I had described it in this format, and I can give you a more formal definition if people are interested in. So basically, you can think of them that there are n inputs, x1 to xn, and inside them there are 3 kind of gates. One of them is the OR gate. I mean, there are the AND gates and the NOT gates. So you can talk about this thing as an directed acyclic graph with 3 kind of vertices. With vertices, what are the vertices? One of them is V, which is the set of variables. So basically it is x1 to xn. There are the OR gates. So maybe the gates, say G1 to G some T. These are the OR gates, maybe OG to OT. Then the AND gates, AG1 to AGT, AG something, AGK, and the NOT gates, say NG1 to NGR. So there are this set of vertices are there, and the idea is that any of these OR gates, so for OR gates, okay, and AND gates, they have to have in degree exactly 2. In degree equals to 2. So that means there are 2 edges that goes inside. They might, I'm not saying that, so it can be have something like this, say, and so this is xi plus 1, and then there might be an on NOT gate, and this can go into an OR gate. Okay, so in some sense they're all directed, right? So they have to have an in degree exactly 2, and the NOT gates have in degree exactly 1. Now it can have multiple out degrees, that we don't care. And then the final thing is this output gate. There is an output gate, maybe you could call it O, and it has one output. And what we are interested in is there a setting of variables, meaning xi to true or false, such that the output is true. So this is the question. This is the input. Input is this directed acyclic graph, right? Which you can think of it as a graph, you can think of it as a circuit. That's up to you how you want to think of it. There are inputs which are basically variables. Inside them, there are only AND, OR, and NOT gates, right? And your job is to check whether the output can be made to true or not. So this is called the circuit SAT. Now this is also an NP complete problem. Okay, so now I'm going to talk about another SAT problem.
Sir, just to verify,
Yeah.
the input x1 through xn can have multiple out degrees as well, right?
Yes. They can also have multiple outputs. Yeah. So
Okay.
x1 can go to here and here. I mean, not here. Yeah.
Okay.
Yeah, it can be something like this. Okay.
Okay, sir.
Out degrees are all fine. Yeah, and also this, yeah, you are right that I have not written the x's have out degree in degree 0. I mean, they don't have any in degree. I mean, that is like kind of obvious thing. So that's right? So there's nothing that the variables take. The variables are all variables, and that is it, right? Fine. Okay. Now, another thing that is used is what is called a CNF formula. How many of you have heard of CNF? Has anybody of you have heard of CNF?
It's the normal form, right? Chomsky normal form.
It can be called Chomsky normal form or conjunctive normal form. Yeah. Now, what is that? It is nothing but a formula, which basically means that you can think of it as, so here we are talking about only degree 2 input, right? Now, why are you talking about degree 2? Why can I not or have more than 2 degree? Why cannot and have more than 2 degree? Yes, you can have that kind of a thing also. You can remove this particular thing and say that, okay, or gates and AND gates can have multiple degree. That also is a valid problem, and they are actually, again, both of them are almost equal for complexity purpose. So in this Chomsky normal, the conjunctive normal form, it is AND gate. So this is an AND gate or AND gate, okay, of OR gates. That's it. And of OR, and then there are the variables. Okay, I mean the variables can appear multiple times, x1 to xi. Maybe this one is x1, x3, x5. They can something else. So it is this is what is called a formula, which is an AND of OR thing. Okay, so we can write it as AND of OR of something, or sometimes it is written as, say, x1. No, and then there are some, so these are not x1 to xn. They can also have literals, meaning some of them can be negations. So it's x1 or x2 or x3 complement and x1 or x4 or x5 and something, and doesn't have to necessarily be all three things. X2 or x3 complement or x4 complement or x5 complement and so on. So this is, so such a thing is called a normal form, a conjunctive normal form. AND of OR is called a conjunctive normal form. Now it so turns out that any function, now this is something comes down from the world of logic, that any function or any truth table or whatever you want to call it, or any function from true false to the power n to true false can be written as a CNF. You can go and try to prove it yourself.
So true false to the power n means
It's a function.
end of some.
It is like
end
the
of-
variables are taking the n variables. Each of the variables can take and or
Okay.
true or false, and it outputs a true or false statement.
So, what is this theorem called?
This is not called anything. This is basically what is called as the universality of CNFs. It is very easy to prove it. Okay, just think of what a CNF is and you will understand it. Because, I mean, what does it mean by this function? Okay, if I give you a function f from true false to the power n to true false, what does it mean? Right? Well, okay, there are some set of things that outputs true for some set of inputs it outputs true, right? Yeah. So now I've been given a particular say. So let's look at all the possible terms that outputs true. Okay, so that means I have x1 to xn. Okay, if I put this to be true, this next one to be false, this to be true, this to be true, this to be false, this to be true, then output should be true. How can I encode this statement as a thing? Okay, how can I encode it?
X1, X2 bar, X3, X4,
X1,
X5 bar.
what is in the middle? And, right?
Yes,
Okay.
and
X1 and X2 bar and X3 and something, right?
yes.
So this basically, this simple formula, this is just an AND function that basically says that if the input is like this, then the output is true, right? Okay, now let's take another one. Maybe I have another thing that true, 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 false, true. How can I do it? Okay, I will also write the same thing, x1 or x2 or x3 or x4 or x5 complement or something. I'm sorry, and all of them. So this will encode that if this is all of them, then output true. So at the end of the day, if I put an OR on all of them, so OR on all the encodings of true instances, all encoding, so encodings of all the true inputs, encoding coding of the instances of F inverse true, then I will have that function. So F is exactly this. Is this clear?
Yes,
Hello?
sir, yes. Yes.
Okay. So F can be written therefore as a CNF. No, it's not a CNF. Sorry, I made a mistake. This is a OR of AND.
Yes, but we can similarly see all those mappings which map to false and then just
Right.
take the complement and get it.
Exactly. So this is what is called, this is called a DNF. Just like the earlier one was called a CNF, this is called a DNF. And this is called disjunctive or normal form. So both of them are normal form because they are AND of or of AND. Right? Now, interesting factor is that what is F bar, complement of F? This is a or not of or of AND. Now, if you remember your high school or a set theory results, then not of or of AND is nothing but AND of or. Not of AND of or can be written as or of AND. Okay, so F bar can be written as a CNF formula. But what was F? F was something, F bar was something. So I could have started with encoding F bar and then taken a negation of that, and I would have got a CNF. Is this clear?
Yes, sir.
Yes, sir.
Okay. So anyway, so this is not something non-trivial stuff that I'm doing. I'm just saying that any formula can be written as a CNF formula. Okay. Now, this thing, the fact that the SAT is NP complete, okay, as okay, this can be extended to say something few more stuffs. Okay, namely, this is called the CNF SAT is NP complete. What is CNF SAT? The input is a CNF formula. and output is exactly how output is one or true if there exists a setting of variables that outputs true. Now you say that, okay, so I mean, why is this important? Now, what is important is that, see, what is the meaning of NP complete? NP complete meaning that this is hard, or this is the hardest function to do, right? Hardest means what? Hardest in terms of what? The size of the input. So if you remember in the last class, we proved that we gave you an example and I kind of tried to give you a algorithm which showed that primes is in P, but that was not correct. You guys remember that?
Yes, sir.
Why was it not correct? Primes
Because
yeah, go ahead.
because the input in that case we are thinking not of terms of n, it would be log n, essentially the
Right,
size
because
of
the
big array.
input size was log of n, right? And there I did not tell you one thing, and nobody of you kind of stopped me there. When I told you input size, I told that, okay, input is n, of course, input is at, what is the, sorry, oh god, what am I there? Sorry. Yeah, so the input was n, right? And the input size was log n. But input size is log n when? When is it true? Is it actually true? Do you think that input size is actually log n?
Yes, because we use binary encoding, it will be log.
Yeah, this is only true when we are using binary or decimal encoding. Right? If I use unary encoding, what people used to use in long days, n means I have to give you n objects. Then the input size is not log n, right? Then the input size is n. So in case of unary encoding, input size is n. So in that case, it becomes trivial. So although this concept of primes was given to you, I defined the language primes, but the problem gets only properly defined when I tell you how the input is given. Is the input given as a binary or is it given as a unary, right? And if you convert them, every binary letter can be written, every binary number or every number represented in binary can be represented in unary also, right? So now it's like, okay, so it depends upon how it is given, right? So if somebody gave me in unary, then the algorithm, then the problem was in P. If the input is given in binary, it is NP complete. So what am I saying? It is not in P, not NP complete. It's not obviously in P. I mean, it's not obvious that it is in P, right? So similarly here, just because circuit SAT is NP complete, and any circuit SAT is basically a function that can be written as a CNF formula, doesn't mean that the CNF SAT is also NP complete. Okay, because there can be a blow up, right? So what I'm trying to say is that we do have, for this particular case, we do have circuit
Sir,
SAT.
can you just repeat the last statement regarding SAT and CNF SAT?
Okay, so let me put you these three statements, right? Circuit SAT is NP complete. Okay. Every function can be written as a CNF. From these two statements, statement 1 and statement 2, can I say that means that CNF SAT is NP complete? Can I say that?
Yes.
So because the CNF set can be reduced to circuit set, right?
But there is a change of size.
No, you mean circuit SAT can be reduced to CNF, not the other way around.
It
right?
is not obvious, right?
Like,
I have told you that how to write a function as a CNF,
yes.
but how big was it? How big is the circuit? How big is the CNF? The way in which I have at least proved to you, it is 2 to the power n.
Yes, 2 to the power n terms will be there.
So the blow up of the input is exponential. So it is like, it is exactly what I was trying to say, that primes in binary may not be in P,
Sir.
and
I have a
any
question.
binary letter, any number can be represented in unary. Does it imply that primes in unary may not also be in P? That is not the case, right?
But sir, in the CNF, can you just go back to the CNF section again? Why is the input size 2 to the power n here? We are taking a n length x1 through
Yes,
xn.
exactly.
Right.
So what is the
Not
input
2
here?
to the power n.
What is
Our
the input
function-
here? In a circuit set, what is the input?
N
N.
length bit array 1 or 0, each element containing 1 or 0.
Hold on. What is in a circuit set? What is the input?
N. We'll be giving n variables, so n, the input will be of size n.
Okay, no, it is more than n. What is it that we are giving? We are giving this graph, this circuit. Right?
So,
Yeah.
Okay, the circuit is also being considered as an input here,
Yes,
right?
of course, because the circuit is massive. The
Okay,
circuit is of size 2 to the power n. Then it is a trivial thing.
but why would the circuit be considered as the input? We have a circuit, and
No,
for
we
that,
don't have a circuit. What do you mean? What do we have a circuit?
like, the function will be given to us, right? The circuit is
How
the
is the
function.
function given to you?
So the
That's the point.
satisfiability check depends on both the bit string and the circuit. So
Yeah. You have been given a circuit, and question is that is there a way of fixing the variables that the circuit outputs true?
Yes, so we have been given a circuit, like.
So that's the input. How will you fit this whole machine? How will you fit the circuit to the algorithm?
So, say, going back to some other NP problem, say the traveling salesman problem.
Yes, yes.
In the traveling salesman problem, the graph will be given to us, and we need to find a path in, say, polynomial time that reaches all vertices.
Polynomial in what?
Polynomial in the number of vertices.
Polynomial in the size of the input. The size of the input. What is the input? The graph,
Okay.
right?
Okay. So here, polynomial in the size of the function, we need to find a.
Find the size of the circuit.
Okay, polynomial. So if a circuit blow up occurs,
Then
even
it
the
might become
circuit.
very trivial. Yeah.
Even though circuit SAT is an NP problem, if a circuit blow up occurs, the CNF will turn out to be a polynomial problem.
Maybe it can become a polynomial thing, right?
Yes, maybe.
so just to verify here,
Yeah.
for the SAT, we are given a circuit and we can try to check whether there is any n length
Right.
bit string which
Yes.
satisfies the
Right.
circuit, right?
Right.
Okay.
Yes. So for circuit SAT, you have been given a circuit. So maybe this is something I should write again. So for circuit SAT, what is the input? The input is the circuit. Okay, so circuit, I call this one C, and the output is 1 if there exists a setting of variables, or if you want, you can write it as here circuit and the variables v1 to vn, setting of variables such that the output is 1. So the size of the circuit SAT input is size of the circuit plus size of plus n. Okay. Hello.
Yeah, okay, sir.
Yeah. So in the case of CNF SAT, it is exactly the same. What is the input? The input is the variables v1 to vn and what we call as the clauses. What are clauses? So when I define you this thing, right, each of the internal and things, this one is clause 1. This is one clause. This is a clause. Each of the or is a clause. Okay. So in fact, what we usually represent is that there are m clauses C1 to Cm and n vertices, n variables v1 to vn, and the output is exactly same, is 1 if there exists a setting of variables such that v1 to vm, sorry, such that the output is 1, or this of the CNF evaluates to 1. Okay, now of course, this is an easier problem than this. Clearly, because a CNF SAT, a CNF formula is also a circuit. Okay, but a circuit, but as it turns
A
out,
CNF formula is not a circuit, right? Because circuit limits us to 2 inputs.
okay, so it has a binary thing.
Yeah.
Okay, just 1 second. Just 1 second. Hello. Hello. Hello, can you hear me?
Yes, sir. You're audible.
Yeah, sorry. Yeah. So okay. So you are correct. Somebody Devoshi pointed out that as I have described, the circuit set has this AND and OR in gates, which have only input 2, and this one has allowed multiple things. So in some sense, you are right. These two things are not comparable immediately. But it so happens that both of them are actually NP complete. Now, this is something I am not going to prove it again. Circuit set was the first thing that was proved to be NP complete. And it can also be shown that CNF is also NP complete. Or in other words, any circuit can be written as a CNF without a more than a polynomial blow up of size. So both of them are NP complete. Okay, and now there is a simple thing that is asked is that what happens if you add more restriction to the circuit? So one of them is what is known as one of the most popularly used thing is called 3CNF. What is 3CNF SAT? This is exactly CNF SAT where you are restricted that each clause has less than or equal to 3 variables or literals. So what is a literal? A literal is basically an xi or a xi bar. This is called a literal. Okay. So for example, here in the example that I have drawn, where is it? So here, for example, this will have a lot of literals, right? So this clause have high size. But you can write this one as clauses of small sizes also. And actually, you can prove it by a little bit of way that even 3CNF is also universal. Any function can be written as a 3CNF formula. And this is also NP complete.
Hello, sir.
Yeah.
I'm having some trouble understanding these
Sure.
two things. So why is not the circuit set not equivalent in some sense to 2CNF set? Because it is essentially we can think of the circuit set as evaluating 2 literal clauses at every stage, right?
No, hold on. Not 2 literal clauses. Okay, why not? Because in circuit SAT, right? For example, think of this one. Okay, I give you this example. Say OR of, no, sorry, and of or, both of them are say or of, say this one is say x1 x2, this is a x2 bar x3, and so on and so forth. Okay, the x1 x3 x3 x4. How will you convert? This is a OR of AND of OR of variables. This is a circuit.
Yes.
Now, why is this not a? Is this a 2CNF?
Yes.
Yes, I think.
Okay.
Yes.
Why? You have to give it as an OR of AND or AND of OR. I mean, you can write as 2CNF of, or you can write a 3CNF of this.
Okay, so the
Because any circuit can be
CNF
converted CNF.
Sorry?
CNF contains essentially 2 layers only, you are saying.
Yes, just 2 layers.
Okay, okay, I did not get that point.
Yes, CNFs are just 2 layers. So not CNF, it's a normal form. Any normal form has just 2 layers. CNF is AND of OR and DNF is OR of AND. That's it.
But sir, you said every function can be written as a
It can be
CNF.
written. It can be written, but there can be a blow up of size. So how it is this one written? If I have to write this one as a formula, let's write it this way. This is a formula in which I have to first say, okay, take x1 or x2 and x2 bar or x3, right? This is this part done. On this part will be this whole thing. I have to take an or, and I have to take it as x1 or x3 and x3 or x4. So this is the formula that has been given to you. But is this written as an or of n formula? No. Can you write it as an or of n formula?
Yes, we can write it as
some
an or of
dummy
n.
variables.
Sorry?
We can
By
write it
using
as an or of
dummy
n form.
variables.
You can use dummy variables, or you can just use it as a, you remember the De Morgan's law?
Yes, expand it, just expand
You
it.
can expand it, right?
But then the input not be 2.
Then the
Yeah,
input
cool.
will not be 2,
Yes.
right? And so you slowly create a formula. Okay, you can write this one into a CNF formula. It is possible, but there will be a blow up of size. Number of clauses might be lot. Okay,
But sir, you
so
just
by
told that,
unfolding, yeah,
like, you just told that for any circuit or for any function, when converting to CNF form, the blow-up will be polynomial in nature.
yes, you can do it with polynomial in nature also. Yeah, that's non-trivial. Okay, that reduction is not that easy.
Yes.
Okay, you can do it with. Now from CNF also you can go to 3 CNF using what one of your friend was saying, using dummy variables. Okay, so maybe
But-
this is an exercise I can give you guys to
But
try.
why is 2 CNF not NP complete, or why aren't we considering?
Yeah,
2?
so good. So I will come to that. Yeah, I was going to tell you. So, but for you guys, why don't you guys take this particular example and try to write it as a CNF formula, and then try to write it as a 3 CNF formula. Okay, and you see how you can do that. Just for this example, you will understand how you can end up writing it as a 3 CNF formula. Okay, so this is an exercise. No, this is not good. So you will slowly understand how you can convert a formula into a CNF formula and then proceed. Now it so turns out that when you try to, now question is that, oh, why not try to do it with 2 CNF? Okay, it turns out that you will not be able to do. Okay, convince yourself that not all, you cannot prove it exactly, not all 3 CNF can be written as a 2 CNF of polynomial size. Okay, so it so happens that when you move from 3 CNF to, so when you do this conversion, okay, you can prove that this will not blow up. It will be a polynomial size increase. Okay, when you do this one also, you can do a polynomial size increase. But when you write it as a 2 CNF, then it will have an exponential size increase. Okay, and this is something very crucial. This is something similar things happens in the case of the primes. Whether a number has been given as a decimal or a number has been given as a binary, the number of bits required is log n. But from binary to unary, number of bits required suddenly becomes n. So there is a threshold beyond which the input size can grow. So what you will be able to, so you can take these 3 things as a God-given truth. Okay, if you are interested in knowing more about it, you can, I mean, I can take a separate class or something like that, more how do you prove this statement. But for now, please take them as God-given truth. Not only this one, I have also written the another one, that ILP.
What about 2CNF set?
I will come to that. Yeah, so ILP, circuit SAT, CNF SAT, and 3CNF SAT, all of them are NP complete problems. Now, what happened to 2CNF SAT?
If the blow up is exponential, then it is a P.
I mean, that is, I mean, see, how do you prove that blow up is always exponential? You can say that, okay, I have come up with the conversion and that is exponential.
If we show for 1, is that not a contradiction?
No.
Which is enough?
No, not at all. It's an like the algorithm thing, right? You're like an encoding. You have shown an encoding that makes exponential blow up. That doesn't mean that no other things exist. So that's why I did not show that. Try to convince yourself. You cannot prove it. I don't even know the proof of it, honestly speaking. They cannot have proof of it. But what you can prove is that 2CNF is in P. This is also another exercise. Okay. So if I give you a 2CNF, a formula where every clause has exactly 2 variables, prove that you can solve this whole thing in polynomial time. Okay. Now, you say that, so 3CNF is NP, 2CNF is P. Does it not mean that 3CNF to 2CNF there is an exponential blow up? Right?
Of course.
But the problem is that I come back to the statement again that I told you. I don't know whether P is equal to NP. Not known. It's very well possible that they are equal. We don't believe it is, but we have not a proof of it. Okay. So if actually P is equals to NP, it would mean that you can reduce a 3CNF to a 2CNF in polynomial blow.
So just going back to something,
Hmm.
Every CNF can be reduced to a 3CNF in polynomial blow up.
Blow up, yes.
Okay.
Every CNF can be reduced to a 3CNF into polynomial blow up. Okay, you can prove that one. Now, okay, so this was how about the setting of the problem. Okay, so for now, this is all that I want you guys to remember. That here there are 4 objects that I have given you, 4 problems that is known to be NP complete. Of course, we know a lot more things are NP complete, but for the part of this class, let's say that these are the 4 problems. Now, imagine, try to put yourself in the shoes of a researcher or a person working in an industry or something. And somebody comes up and tells you about a problem, namely vertex cover. What is vertex cover? Vertex cover means you have been given an input. What is the input? A graph G. And a K. And the output is 1 if there exists a vertex cover, or meaning there exists a W subset of the V such that W of K is less than or equal to K. And for all UV in G, in E, all the edges in E, this set UV and the set W is not empty. So that means at least one of its endpoints are in this set. So there are a set of vertices such that every edge in that graph, has a is a neighbor of the vertices in W. Have you guys seen this particular problem anywhere else or before?
Yes, sir, we have taken graph theory. Most of us have taken graph theory.
Okay, good. So you have seen this one, right? Good. So how will you attack this problem? So this is something that can come in the class or exam. Okay, so that's why I'm doing it. And I will give you a problem and I tell you how do you attack this problem. What are the steps will you follow to solve this problem? Someone? Maybe Akshay? Akshay, are you there?
Yes, sir.
Yeah, how will you go about it?
So, other than the brute force, we can think about dynamic programming, right? We have been doing that.
That is if you want to try to solve it, right?
Okay, yes.
So we can, in some sense, try to reduce it to circuit set. Suppose we allocate some bit to the where a bit string for
Right. So
the length
yeah,
of vertex, and 1 if they are in vertex cover, and 0 if not. Sum of ones must be less than k, and we can, if they are in neighboring, we can take end and
yes, hold on,
evaluate.
hold on, hold on,
finally.
hold on. Those you are going a bit fast for me to understand what's going on. But I think you are going in the right direction. But let's so let me go by step. Okay, some of the steps I will not do. Okay, of course, first thing you will try to solve. Let's say in polytime, and let's say you have failed. Okay, let's say you have failed. Okay, then what? Then the next thing to do is that okay, you cannot solve in polytime. Let's ask, is it in NP? Can you solve this question?
Hello?
Yeah.
It is in NP, sir. That
Okay.
is-
Why is it in NP?
If given a solution, we can easily verify.
Okay.
If-
Given a solution, you can easily verify. So what is the solution? Solution will be this W, right?
Set of vertices.
And then you will basically end up checking whether this condition satisfies or not.
Incident or not.
Good. So if it is not, if it is in NP, the next thing is that to ask, is it NP complete? Now, one way to do it is to prove it by reducing it. So let me give you a reduction for it. Okay. So I've been given this graph, right? What I will do is that I will write a linear program. Okay. So I'll put some variables. Okay. So I will have used some variables, say x1 to xn represents. So these are basically, I would like to think of it as this will be 0 or 1 kind of a variable, such that xi is equal to 1 if the vertex vi is in the W. And I want to minimize summation of xi such that what? Such that for all uv or all say v1 vi vj in the H set, I want to look at these two neighboring these variables corresponding to two neighboring things, and I will say this must be more than or equal to 1. And when the xi's are 0 or 1, right? Or maybe I can write it like this: xi is bigger than 0, less than 1, and the xi's are in integers. Now note that a solution here would be what? You have some set of variables. Each variable I'm thinking of as corresponding to the vertices. Each vertex each variable is 0 or 1. If it is 1, I will put them in W. If it is 0, I will not put them in W. And the idea is that for every age, this one is ensuring that at least one of them is in my W, which is the basic definition of vertex cover. And I am trying to minimize the size of the vertex cover. So this is my ILP. This is my ILP, right? So I have written this vertex cover problem as an ILP. And since I know ILP is NP complete, I'm done, right? Is this reduction clear? I'm not getting hearing.
Sir, I cannot understand why you write xi belongs to 0 to 1.
No, I want xi going to 0 to 1. Xi is a variable that is an indicator variable kind of stuff.
It can take either 0 or 1.
Yes.
But you wrote 0 less or equals to xi less,
So
less or equals
think of these two things. These two means what? What does these two combination mean? Xi the integer value.
Yes, sir. Yes, sir. Yes, sir. Got it.
Kulkal Pramanik, are you there?
Yes, sir.
Is it clear to you?
Yes, sir. Yes, sir.
It's clear to you, right?
Hmm.
So this is giving you a proof of vertex covered is NP complete, right? Shohan Das,
Yes, sir.
yeah. Is this reduction clear to you?
Sir,
Yeah. Tell something. Sohan,
no, sir, it is not completely clear to me.
okay. So can you tell us? I mean, are you in kindergarten or what? So I have to ask you guys individually, and only then you will tell me that something is not clear or something is clear. Can you tell me which part is not clear to you?
We are minimizing the sum xi.
Yeah. So this one, forget minimization. Look at this thing. If I think of the bottom part, if I can solve this problem, if I give a solution that satisfies all these constraints, will I get a vertex cover? I mean, I will take only those vertices for which xi has been put to be 1. So these two sets basically says that xi can take only 0 or 1 value, right? My idea is that I will take only those xi's which have evaluated to 1 and my vertex cover. And this basically says that look at all the edges. At least one of the endpoints must be there in my vertex cover. So this chunk basically says that any solution to this chunk is a vertex cover. Is that clear?
Yes, sir.
Okay. So this chunk says that, okay, find me a vertex cover. And this says that, okay, find me a vertex cover which is minimum, which has minimum number of vertices.
Yes, sir, it is clear now.
Okay. So can you tell me what is clear?
Sir, from the
What
lower
is clear?
from the lower part, and we are finding minimum vertex cover. So
Yes.
from the lower part, we are finding some vertex cover, and then we are taking minimum of among all the vertex covers.
Yeah. So if I just ask the question that does this ILP has a solution less than or equal to k, that would give you an answer to does the graph has a vertex cover of size less than k, right?
Yes, sir.
right? So if the ILP has a solution less than k, this implies that the graph has the vertex cover of size less than k. So I have reduced the problem of vertex cover to ILP, right? Debashit, do you have any comment on this?
Sir, one question I had was that the 0x, like the breakdown we did for
Yeah.
0xi1 and xi belongs to z,
Hmm.
that is to satisfy the integer programming formulation, right?
That is the integer
Rather than
variable.
just one.
Otherwise, we don't know how to make sense of if somebody
The xi
somehow I
belongs
get
to 0, 1.
yeah xi is 0.5. What does
Yeah,
that mean? I have to make sense of this variables, right?
So like instead of writing xi belongs to set of 0 and 1,
Yeah.
the formulation is essentially for the
Right,
constraint.
right. For the ILP.
Yes, and what my solution was essentially the xi plus xj greater than equals to 1. I express that as a OR gate, and then for the for all part we take the AND gate, and that would
Right.
give the
Okay,
bit
yeah,
string.
that is completely right.
Yeah.
But think again, all of you please think, what did we end up proving? Does this imply vertex cover is NP complete? This is a mistake that I have seen even senior faculty members making.
We have reduced the vertex cover to an ILP.
So which is harder? Which is harder? Think of it this way. This basically says that if I have an algorithm for ILP, I can get an algorithm for vertex cover.
But we have to show both direction, right?
At least what has been shown till now.
Yeah, we showed this direction only. Yes.
We have shown that if I have a solution for ILP, then I have a solution for vertex cover. Or in other words, we have
ILP
shown
is the tougher problem.
ILP the tougher
Tougher.
problem, right?
Yes.
ILP the tougher problem. ILP the tougher problem. ILP is NP complete. Doesn't mean that this is NP complete.
We can't say that, sir.
We cannot say that as of yet. This is not true. We cannot.
But if we show the other direction, we only need to show the other direction, right? Then
Yeah, we only need to show the other direction. But how would you show the other direction? This is the
yeah, like
yeah. Go ahead.
by the same thing we can do, right? If we have a vertex cover, so this is the problem. We changed the reduction is actually sort of an equivalent statement, right?
No.
First, we need
Look
to
at it.
define what the ILP problem is, right?
Yeah. So I have made a function, a reduction from the vertex cover instance to the ILP instance. Right? That doesn't mean that F inverse is a so what I need is the opposite. What I need is a reduction from an ILP instance to a vertex covered instance.
So for ILP, if you get x1 to xn, we can
Yeah.
define the
Well, no.
vertex.
How will an IPLP have only this kind of structure? Who has told you that ILPs only have this structure?
Exactly. So we have to first define a proper ILP and then
You have
think
to take
about.
up for any ILP, right? This is a very crucial point. Okay.
Here we
This-
have only two values for xi, but in general ILP will have any k.
In general,
value,
ILP will
right?
have different things. In ILP, we will not necessarily have just only one addition. It can have multiple additions.
Yes.
It can have for some real value, some linear, any linear combination is possible. Here also any linear combination is possible. Okay. So this is something that you have to be very careful of.
So for linear programs, there is something called like standard form and
Even standard forms, these are all standard form things also, but they are not of this structure.
so if maybe we can convert the ILP into standard forms, something
Yes,
like
you can start with the standard form.
and then we can
Even
move
then,
to-
that is, I mean, of course, it can be done. Okay.
Okay.
But that is not trivial at all. By no means is it trivial. Okay, so okay, first things first. Whenever you do this reduction, this is not useless. Okay, what you have done is not useless. This has shown that vertex cover can be reduced to ILP. That doesn't mean, sorry, not vertex cover, vertex cover can be reduced to ILP. That means that if I have a solution for ILP, I can have a solution for vertex cover. This does not show vertex cover is in NP complete, but what it does show, and this is something also very important, if I have an algorithm for ILP, that algorithm might be heuristic algorithm. Implies I have an algorithm for vertex cover. This is something used a lot. You take this problem, convert it to ILP, and use some algorithm to solve ILP to solve this problem. Now you said, okay, why do you care about it? Because of course, in real life, human beings cannot keep on working on all possible infinite problems, right? Particularly when we know that there are these concepts of the small, simple, I mean, the concept of complete problems. So what as researchers have done in the last 20, 30 years is that they have picked up some problems, some of the central problems, and have tried to come up with crazy heuristic algorithms for them. The two of them that which has been worked on is, one of them is CNF-SAT or SAT, whichever, and the other one is ILP. So this, you have heard of it as SAT solvers. So SAT solvers are algorithms that solve SAT. But SAT is NP complete. So we don't expect these algorithms to be polynomial time algorithms. But they work in most instances. So they are not worst case, they will have exponential time, but for most instances, they do still work. So you can use this kind of algorithms as black box. Another one is the ILP solvers. People have worked hard on it. Now, what are these solvers are? Let me just put it here. None of them, this is important, okay, I should write it the different color. First thing, none of them are polytime algorithms. We don't believe they can exist polytime algorithms because they are incomplete. Okay. Neither in the worst case or average case. In neither of them they can be polytime. But this is something where things are a bit fuzzy. But for most, now these are none of them very clearly stated things. Naturally occurring instances. These solvers work quickly. Now, what does it mean? What do we mean by naturally occurring instances? This is where theory and practice kind of differ a bit. This is the place where it's like, okay, I have this great algorithm. This algorithm somehow magically solves for many instances. But that doesn't mean it solves for all instances. We have not much understanding of what these concepts are, but these are basically for many of you who will be going into non-theory, you will sign them as benchmark problems and so on and so forth. Okay, so in terms of real life applications, they seem to work very nicely. So if you come up with the problem for which in the first step that you have done, you have tried to solve it polytime, you have failed, okay, then you have tried to prove it with NP, you have proved it. Next thing is that you are asking, is it NP complete? Before you can do NP complete, you can do this following thing. So it's the fourth step in some sense. Reduce the problem to ILP or SAT or something, and use the solvers to obtain, I will use this word heuristics, heuristic algorithms for it. This is an upper bound, like someone has come up and given you a problem, say vertex cover problem, and told, okay, I want a solution to it. Now you have understood that, okay, I am unable to come up with a polytime algorithm. Okay, I have been able to say that it is NP. Now should I just give up? So one option is to say that, okay, see, there are the solvers that are there. Why don't I use these solvers and try to solve it using them? Okay, and this will give you a some kind of a sense of an algorithm that works in such that for real life instances, they work. This is something very crucial concept. This is how all the big companies work, because all the big companies, almost all the problems that you will find that we have to solve regularly in real life are NP complete problems. Okay, so this reduction, note that this reduction that we did is not a proof of NP completeness, but this is a proof of reduction of a problem to a standard problem, namely ILP or SAT. And using them, you might be able to come up with some solutions. But having said all of that, I have not yet answered how do you prove that this is NP complete. That is not known. So that is also something that will be required, right? Some client has come up and given you this vertex cover problem, asked you to solve it, and you have given them a solution that seems to work, but not provably correct, or provably always works in the right time. Then you have to kind of tell them that, see, I cannot do this algorithm quickly because there is some hurdle, and namely that problem is actually NP complete. So I have to find NP complete. So now let's try to prove. So how to prove vertex cover is NP complete? Now this is a proving some problem is NP complete is an art in itself. Okay. Note that what do I have to do? I have to prove that vertex cover is less than some NP complete problems. So I have to take up a NP complete problem. I have to take a general instance of an NP complete problem and convert it to a vertex cover problem. Okay, so I cannot start from a vertex cover problem. I have to start from something. Now, depending on, so since we right now know a lot of problems that are NP complete, it all boils down to picking the right problem. So let me prove this thing for you. Okay, this will be a bit involved. So I will prove that 3SAT, I will reduce 3SAT to vertex cover. Okay. So let's see, how will I reduce 3SAT to vertex cover? So what is a 3SAT? So I have these clauses C1 to CM, right? So then the AND of all of them. And each of the clauses, say this is AI1 or AI2 or AI3, right? And there are the variables x1 to xn. And what I know is that this Aij, each of them, is either say maybe some xk or xk bar, right? Is this clear what's going on?
It's 3CNF.
It is 3CNF, not
Yes.
3SAT. I mean, okay, 3CNF is also sometimes called 3SAT. Yeah, 3CNF. Right? So is this instance clear of 3CNF? Okay. Anyways, let me progress. So now what I will do is just following. I will draw a graph. Sorry?
What are exercise?
What are x's? X1 to xn are the variables. I have n variables, m clauses. Each of the clause have 3 literals, right? And the literals, each of them are basically some variable or its complement. Correct?
Yes, sir.
This is just a general instance of a 3CNF formula. I have not done anything.
Sir, the literals can also contain dummy variables for CNF, 3CNF, right?
Yeah, they can contain 1 or 2, you mean, right? If, I mean, fixed variables, true or false.
Yeah.
Yeah, so let's not take care of that. Okay. I mean, you can put them as true and false also.
Okay.
Yeah, you will see that will not matter here.
Yeah.
In this reduction. So what is it that we have to do? Can somebody tell me what is it that we have to do? We have to create a what?
From this, we have to create a graph.
A graph, right? We have to create a graph and a value k and say that okay, k or k is not, so maybe it's L. Yeah, k such that what? Let's better to write it down properly, right? If so this is also called this CNF formula, phi. So phi is this formula. If phi is in 3CNF, if and only if there exists a vertex cover in G of size less than or equal to k. This is, if I can do that, then we are through. Correct? Okay, somebody say yes or no.
Yeah, okay.
Yeah. Okay, so now let me create the graph. Okay, this is called gadget constructions. They can be very tricky at times. Okay, so what do I do? First of all, I make, so for each of these clauses, I will make a triangle. So for the first clause, I will make 3 vertices, say A11, A12, A13, and I make a triangle. Then for the second clause, what do I do? Again, same thing. A1, A21, A22, A23. and for all the M clauses. Okay.
Yeah.
Now, for the variables, I have n variables, I will draw lines. So this is x1, this is x1 bar. This is x2, this is x2 bar. And still xn, xn bar. Okay. Now I will have to add edges between these two. How will I do? So if x aij is equals to xk or xl, then I will add an edge between these two. Okay. And if aij equals to xl bar, then I will add an edge between this. Okay. So for example, if my first clause C1 was x1 or x2 bar or x3, I would have drawn with x1 or x2 bar or x3. So x3 is there. And if I had the second clause as a x1 bar or x2 bar or xn, I would have drawn to x1.
So the last connection was to x3, not x3 bar.
Oh, it's right. You're completely right. To x3, right? x2 bar and xn. Okay, right. Like I will add this whole edges. So this is my graph G. Now let's try to understand this graph. Can somebody say what is the vertex cover of this graph? How low can it get? So see, if you have to have a vertex cover, right, you have to pick up some vertices. Okay. Yeah. Now there are the edges like this. So that means at least one of them has to be there. At least one of these two has to be there. At least one of these two has to be there. Else, how will I cover these edges? Correct?
Yes, sir.
So at least the vertex cover must contain one from each of these pairs, at least one from each of the pairs, right?
Yes.
Similarly, look at this clause thing. This is a cycle of length 3, right? So I have to have two vertex from these two, at least. If I leave, if I have only one vertex, this is my vertex, then who is going to cover this? Correct? So among these three vertices, at least two of them has to be there. Similarly, for these three vertices, at least two of them has to be there. Similarly, for these two vertices, at least two of them has to be there, right? So we can say this is an observation in some sense you can think of. A vertex cover of G has to have size at least how much? One from the top one, so n, and two from the bottom ones. So 2n plus, sorry, n plus 2m, right? It has to have this much size. Okay. Now for me, I have to define this k, right? This k that I have to define. What is the k that I will define? I define this k to be n plus 2m. Now think a little bit on this. problem, this design. I claim that if there exists, if the original formula had a satisfying assignment, that means I could have maybe in the satisfying assignments, say maybe x1 and x2 and x3 bar, x3 and n bar was set to true. Whichever things are set to true, right? I would have picked I will pick them as my vertex cover. What does it mean by this is a satisfying assignment? This is a satisfying assignment meaning in each of the clause, right? At least one of them has to be touching it. Means x1 is true, meaning acha. So that means x11 is true, right? So this edge, so for every clause, at least one of these edges is taken care of. So in that case, I would pick the other two edges, vertices in my vertex cover. Convince yourself that this
Sir,
is a valid vertex cover of the whole graph.
So can you
Yeah.
repeat the guarantee that one of the among each clause at least one literal would be covered by one of the edges?
Yes, at least one literal has to be true, correct? So say for example, this edge, this clause.
Yeah, at least two literal has to be true, that I got. Like in each clause, at least two literal has to be
No,
like,
no, at least one
selected
literal
in
has to be
vertex.
true. At least one literal has to be true, right?
For the CNF, but here for vertex cover, at
For
least two-
vertex cover, that means at least, so say x1 is true, that's right? If x1 has been made to true, that means a11 is true, right? That means the vertex, this edge is covered already,
okay,
vertex cover, right?
okay,
So I will pick the other two in my vertex cover.
okay, okay, okay.
Okay. So I will pick the vertices that are true, and if x1 is true, then in each clause, one of the edges, each clause has three edges going out, right? At least one of the edges is taken care of by the variables. I will take the other two vertices.
So this last guarantee that at least one of the edges vertices
true.
is taken care of by the variables. Why is that true?
Okay. What does it mean by a CNF being true? What do I mean by the CNF is true? It's
So
a OR of,
one of-
it's an AND of OR, right?
Yeah, one of the literal essentially has to
Has
be
to
at
be
least
true.
one of the, yeah,
At least one of the literals has to be true, right?
yes,
Which is the literal? So these are the set of variables, right? I have set x11 equals to x1 is true. x1 corresponds to a11.
so x1 being selected in the vertex covered
Means
would
that x1 is
imply
true.
that x1 is true. Okay, okay. Okay, now I got it. Yeah.
Okay. Yeah, I mean, just go and think a bit, you will understand this thing. Yeah, okay. You just have to convince yourself that if I have a vertex cover, if the formula is true, then this is actually true. Then this one has a vertex cover of size n plus 2m. And the opposite is also true. If there exists a vertex cover of n plus 2m, which means that exactly one from each of them and exactly two from each of them, in that case also, it's the set of the variables that we have selected in the, or the literals that we have selected in the vertex cover, okay, one from each of these variable pairs. If you set them to be true, you can prove that that is a satisfying assignment for the formula. So what you will get is that the formula is true or is satisfiable if and only if this graph has n plus, it has a vertex cover of size n plus 12. Now that means I have started from a vertex formula, created a graph, and now I am proved that this graph vertex cover is same as harder than that of a 3CNF, which means that we have proved that 3CNF is harder than vertex covered. And since I know the 3CNF is NP complete, therefore vertex covered is also NP complete.
Sir,
Yeah.
What is the vertex set size here?
Yeah, so tell me, what is the vertex set size?
It's 3M plus 2N, right?
Yes,
Right.
that's it.
But actually, I'm not getting AIJs are X or X bar, right?
AIJs are vertices, okay? So I have, for each clause, I have
AIJs
created,
AIJs are XIs are
I mean,
XI
there are
bars,
two
right?
ways of thinking of it. For each clause, I have, for each clause, I have 3 vertices. Okay? So AI
Okay, but they are XIs are XI or XI bar, right?
in
Some
the
XI or some-
actual formula, yes.
So
They are not exact. So there are vertices correspond to variables, and then there are vertices correspond to clauses. This vertex is not same as this vertex. No. There is a vertex called A11. This is the first literal of the first clause. A vertex corresponding to the first literal of the first clause. Now, if the first literal of the first clause is x1, then I'm drawing a H between x1 and A1. So
Sir,
yeah.
so for the variables, if we select them in the vertex covered,
Yes.
it is essentially 1. Like
Yeah.
if xn bar is selected, then xn is coming as 0 and xn bar is
Right.
getting 1.
Right.
And for the literals, if we select them in the vertex covered, they are evaluating to 0 in the 3CNF, right?
If I mean, see, for each of the variable, right? So I am going to either pick this or this. If I pick this, that means I am picking up x1. That means x1 is true. If I am picking up this one, then means x1 bar is true. That means x1 is false.
Yeah, that I got. But for the literals, the AIJs,
yes,
if they are selected in the vertex covered, they
right.
are
Right. That's
getting the
true.
value
That,
0, right?
they are not necessarily, yes, that's correct.
And the second thing is that for the n plus 2m construction, it can also we can also get a case that x1 and suppose in this example, x1 and x1 bar both are selected.
Yes.
And do not
Yes, that
select
is possible.
A1
So that is possible. There can be multiple different vertex covers.
And we can always get one of the cases that would satisfy the
Yeah.
conditions that we have.
Right.
Okay. Okay.
Yes, there can be multiple different vertex covers. You're right.
Okay, sir.
Because in a single clause, more than one literal might be satisfied.
Yes, yes, exactly.
Okay, so I mean, I'm sure many of you are confused. So please go back and try to solve it for yourself. This is actually one of the easier construction of NP completeness. Let me put it this way. Okay. We will be giving you another problem set with a lots of other reductions. Okay. Now the reductions are a complicated thing. As you can see, even for the simple things, the reductions are not at all trivial. Okay. This is actually easy. But more than the reduction able to do, I am more worried about the fact that whether you are doing the right reduction or wrong. So I will give you a list of problems about these reductions. I will try to post it out as soon as possible, maybe today or tomorrow. And remember, there are two things for a do you do with the problem. You kind of can reduce an NP complete problem to it. In that case, you end up proving that problem is NP complete. Or you can use an NP complete problem to solve it, like we did in the case of the using ILP to solve it. That's not a reduction, that's not proving anything, but that's you can think of it, that's using an solver of a standard problem to solve a problem, solve a NP complete problem or solve a hard problem. Both of the things are important. Both of them are important. So if you want to reduce one to the other, think a bit. What you want to reduce to what? And what should you start from? Okay. So if you want to prove a particular problem is NP complete, you cannot start from, oh, let's start with an instance of that problem. No, you start from an instance of a NP complete problem and then reduce it to construct an instance of the problem that you are solving. Okay, so I think it is going on. Yeah, go ahead.
So the assignments are still like we can skip one of them, right? Like 3 out of 4 or something like that.
I don't know, honestly speaking. Why? You have not solved it yet.
No, I'm still doing the DP assignment. So
I suggest that you do the DP because I am not going to keep my word on this. Because I am very much unhappy with this. I mean, the overall batch's performance, I must say. First of all, the mid-sem was not at all up to the mark. And by looking at I think there are some 8 or 9 people who come to the class regularly. And other than that, people doesn't seem to care. If people don't seem to care, then what can I do? I mean, that's not so. I know that many people have not solved it. The reason I don't give assignments, see, my job is not to give marks to you guys. My job is to teach you guys. And I'm pretty sure other than you guys who come from the class, people are not even listening to the videos. And I am really questioning myself that why am I teaching, honestly speaking. This is very, very, very frustrating. This batch's performance, I don't know how you guys are doing in the other courses. I mean, how was the performance in the mid-sem of the other courses, both for CS and CRS?
For CS, I don't think that we have received mid-sem marks for almost any other subject.
Okay, for almost any other subject. Okay. And is the class attendance for all the other subjects good?
Yes, sir. It's not like this. Essentially, I think online plays a role in the lack of attendance.
That might very well be the case, but I mean, it's not. I mean, like the number has gone down to such a level that this is worse than what it was earlier during the actual pandemic time.
Sir, one more thing regarding CS is up till dynamic programming, most people knew those algorithms and those proofs and methods.
Then why has 14 of the CS people have not submitted the dynamic algorithm assignment?
The assignment,
I mean, that is the case, then why doesn't the CS people have cracked the mid-sem? I mean, all those things are sad, let's put it this way. Yeah. And I know what the people in CS are thinking also, that in the mid-sem, there was questions that came from the problem set and assignments. So this time, that's what I will be studying, problem sets and assignments. But don't worry, this time I will set a question that so that exactly the people who have clearly listened to my classes, they will only understand it. Okay, anyway, so why don't you guys, I mean, anyways, there's some, I think 3 more classes are left. I will, let me see what I will do. If you guys have any questions on this NP complete problems and NP complete reductions and all, very good. I can talk about it more, or I will go into a different topic for the next 3 classes. There will be some assignments and all will be given. Some reductions will be there, reduction problems particularly. Now this is, as I told you, I cannot repeat it. I mean, I cannot emphasize it more, that understanding the complexity of a problem and using other solvers to solve a problem is one of the central problems in any industry, academia, whatsoever. Okay. This is a very crucial thing. And I have seen even some of the senior researchers make mistakes about reductions and all. And if you can look, I mean, this concept of NP completeness, what is NP completeness? NP completeness is kind of a proof that this problem is hard. It's not a 100% proof this problem is hard, but it says that, oh, see, there are all of these other problems like SAT and all of them, for which people have tried for so many years and failed. My problem is also as hard as that. So how do you expect me to solve it? And therefore, I have to come up with a different algorithms, different concept of algorithms. Now, I can talk a little bit of that direction also. What do I mean by different concept of algorithms? But that will be kind of a beyond the scope of this class. That will be kind of an advanced algorithms course. But yeah. So this concept of NP completeness, you can find it in any field of CS, any, be it the systems, machine learning, theory, bioinformatics, anywhere. Almost all paper starts with something like, oh, this problem we want to solve, but it is NP complete, and so we are trying to do something else. This is the basic framework for every quark, even in the industry and all. So this concept, please go and try to understand these things, try them, some of the problems. Okay. How do we come up with a reduction? How do we prove something is NP complete? How do we prove something is, how do you use NP complete problems to solve these problems? Okay. Okay, so I think with that, let me stop today. I think Monday.
So, sir, before we end,
Yeah.
I had a
Yeah.
few questions. First is that I had asked you for some reading materials regarding particularly SAT, and now
Yes.
that we have are also considering ILP, so
Yes.
like formal definitions and basic understanding of those topics.
Yeah.
So if you can refer to that or upload that inside.
Sure. I will do that.
Second is that the reduction techniques, can you guide us to some
Okay, so
reading
reduction
materials? Or,
techniques, honestly speaking, reduction techniques are very vast. Okay. I mean,
yeah,
they're massively hard things. In fact, some of the reduction techniques that are really cutting edge research kind of stuff. If you have heard of this concept of inapproximability, basically, which shows that to some problem is hard to approximate and all, they are also
Yeah.
reduction techniques. So they are also proving some particular problem is NP complete. Okay, then they use very cutting edge work. So reduction technique, there is not any, I cannot really mold it in any way. Okay. For this
But some
purpose of this
pointers to
class,
start with.
yeah, so
like
you can look at
reading.
any of the book will have it, but in terms of this thing, there is this book called Gaddy and Johnson. There's a book by Gaddy and Johnson, rather. It's a called complexity theory or something like that, in some generic name, by Gary and Johnson. Now, this book has one of the best comprehensive study on NP completeness.
Okay.
Okay. I mean, you can look at it. For the purpose of this course, I think some basic graph. So these are called gadgets. Okay, so gadget reductions. I mean, each clause has been replaced by a triangle and so on and so forth. These gadget reductions are very, I mean, to some level, they are not very exciting because they are too magical in some sense. And at the same time, I mean, a magic has its own charm, right? I mean, if you in math, people don't like magic that much. But so yeah, gadget reductions looks like puzzles to some in some sense. It's more like
Yeah.
puzzles than actual rigorous problems. Yeah, I will upload a few examples.
And
of, yeah, go ahead.
lastly, that it would be, I think, beneficial for us to go on this topic for one more class or some more time if possible, because these are new topics for most of us. We have not encountered these things, and like a bit more familiarity of it would be beneficial.
Okay, good. I will do that then. I will take one more class on some other reductions and all those things.
Yeah.
Okay.
Okay.
Yeah. Okay. So do you want to take a, can I take a class on Monday also? Because Monday is a holiday, I think. But
15th is a holiday. So 15th is
yeah. What is
Okay,
15th?
no. Monday only, Buddha Purnima. Yes.
Yeah. I mean, if you guys
Yeah,
are
it should
fine, then
should
we
not
can.
be an issue, I think, for the
Yes,
non.
yes, shouldn't be an issue.
Yes, sir, no issues.
Okay, then I
No
will
issues.
then send a mail and an announcement and have a class in that day also. Okay.
Okay.